Hi. So now that we know what logistic regression actually is and how it is useful for solving classification problems, let's apply it on a dataset which involves binary classification. So I have already imported logistic regression from sklearn.linear model and I have already loaded my dataset for breast cancer which is present in sklearn datasets. This dataset has 569 data points and 30 input features. I have again used model selection for splitting my data into testing and training. So since I have not passed any test size, my 75% of the data will automatically go into training and 25% of the data will go into testing. So to understand this data better, let's check its description. Okay. So it says breast cancer diagnostic dataset. Number of instances 569, which we have already seen, and number of attributes, that is features, there are 30 features. So this is a binary classification problem where the classes are malignant and benign. So basically the cancer is of two types, that is malignant and benign. So this is a data set of 569 patients of cancer which has either malignant cancer or they have benign cancer. So out of those 569, 212 are malignant patients and 357 are benign patients. Okay, so if we see, a data set looks something like this. We have 30 features, x1, x2, x3 till x30. We have 569 data points in total. And our output variable has value either 0 or 1. So our data set something looks like this. If I check my y, it's either 0 or it's 1. 0 stands for malignant and 1 stands for benign. So first let's make an object of our logistic regression class. So I'm naming it CLF, which means it is a classifier. Let's fit our data. Okay, so I'm getting this warning. So just to silence this warning, I'm writing solver is equal to liblinear. Don't worry about this right now. Okay, so I have a few parameters, that is C is equal to 1. In one of the previous videos, we discussed regularization and we discussed a parameter that was C. C simply meant the higher value of C will mean that there will be overfitting, right? So if C is low, then that would mean regularization would be more important. And we have max iterations. This is the number of iterations that gradient descent function should perform to minimize our cost. Then we have multi-class. This we will talk about in the next session. Penalty is equal to L2 regularization. Then we have solver is equal to liblinear, which we just passed. And this is basically the value, that is the difference between the cost function where our gradient descent function should stop, right? So these are some of the important parameters of logistic regression. Next, let's go ahead and calculate the score. Okay, so my score comes out to be 0.944, right? So my score is 0.944. One important thing that I want to discuss, if I run this once again, if I run my code once again, this time my score comes out to be 95.8. Our score will change every time I run my code again and again, right? So why does this happen? This happens because my train test split function, what it does, it always chooses the points randomly. So every time I rerun my code, the points that will be selected for training and testing will be random, right? So different points will be sent to training and testing every time I rerun my code. Hence, the score comes out to be different. If I want that every time same points go into my training, what I can do is pass random state. Random state is equal to 0 if I am passing, or I can pass random state is equal to 1 or any other value. So what this does, If I pass random state is equal to 0, same values will go into training every time, right? Or we can consider this. Let's say you and your friend both are using this model. If you pass random state is equal to 0 and your friend also passes random state is equal to 0, so your training and testing points will be exactly similar, right? So if you pass 0 and your friend pass 1, it will be different, right? So your training points will be different to his training points, but every time you run your code, that is for random state 0, if you run your code, your training points are going to be same every time and your friend's training points are going to be same every time for random state 1, right? Okay, so if I run this code again, now if my score is 95.8 and if I run this again, it will remain same because random state is 0 in both my cases. So in this way, I can get same points to go into training every time, right? Let's say after we study 3 or 4 algorithms, right? If you want to check which algorithm performs better on a data set, you should definitely pass random state, right? Because if you are performing one algorithm on a different training data and other algorithm on different training data, you won't be able to compare both those algorithms as to which one is performing better. So we should always pass a random state. We can pass anything, you can pass 0, you can pass 1, and one very famous value for random state is 42, right? So people generally do pass 42. Now let's see what our predicted values are. So these are my predicted values for my testing data, right? Some of these values will be correct and some of these values will be wrong. So now we have already trained our model and also calculated the score. Our score is fine, everything is good. But one very important thing that I want to discuss is, so this was my y actual, right? Let's say my y predicted looks something like this. Right? So if I calculate the difference between y actual and y predicted, y predicted minus y actual, this is 1, this is 0, this is minus 1, 0, 0, 0, 0, right? So what I can see that for all the data points for which my y predicted came out to be correct, that is this one, this one, this one, this one and this one, my value of y predicted minus y actual will be 0, right? Because both of them are same, so my y predicted and y actual difference will be 0. But for the data points which my algorithm has predicted wrongly, my value will either be 1 or minus 1, right? Okay. So now what I want to know is, for the data points for which my algorithm gave me wrong predictions, that is this one and this one, how confidently it was predicting, right? Let's say if I talk about this data point, if my algorithm tells me that I am 51% sure that it is going to be 0 and there is 49% chances that it's going to be 1, it is saying that if I have to predict, I'll be predicting it class 0, but I'm just 51% sure, right? So I'm not that sure. So in this case, if it makes some mistake, we are fine with it, right? Because our algorithm had already warned us, right, that it is only 51% sure. But had it said that I am 99% sure that it is 0 and 1% I think it could be 1, now this is going to be a huge problem for me. Because now my algorithm is saying it very confidently, that he's very confident that it is class 0, but in actual it is class 1. So this is going to be a problem for me, right? So what I want my algorithm to do is, so for all the data points that it is wrongly predicting, I don't want it to be predicting it very confidently, right? In the same example, if I see, if it tells me that I'm 99% sure that it is going to be class 1, right, for the first data point, If it tells me that I'm 99% sure that it is class 1, but actually our class is 0, so this is going to be a problem for me. Or if it says that I'm 60% sure that it is class 1, we are fine with that, right? Because that's not much of a confidence that it is showing in itself. Okay, so y predicted minus y actual, that is y test, right? So I have this function predict proba, which gives me the probability with which our algorithm is predicting, right? So let's say if I want the probability of my testing point number, this one, so this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So for the 13th point, if I see, my algorithm is telling me that according to me, 78% chances are that it belongs to class 0. So it's not a situation where it is telling that I'm 95% sure or I'm 99% sure, right? So it is still unsure. So still we are okay with that, right? We don't want it to be saying it very confidently, right? Similarly, if I look at this point, so there are 17 in one line, 1, 2, 3, 4, 5, 6, 7, 17 into 7, 119. 8th point, and so this is 127th, which means it is 126 index. So if I look again, it is not very confidently saying that it belongs to class 0 or it belongs to class 1, right? So it's just 64% sure that it belongs to class 0, right? So we are fine with this. So after we have trained our model and evaluated the score and the score is good, so it's always a good practice to see what our probabilities are on some of our wrong predictions, right? So in this case, we have already checked for a couple of them and we are actually fine that it's not saying very confidently. In the next session, we will pick a data set which has more than two classes.